Yeah, yeah, yeah. Thank you, Adam, for your very nice introduction. It's a pleasure to be here and to tell something about solar cells. So for this week, I've tried to wrap up a few things, and the first might not be, let's say, the introductory talk to solar cells, but maybe a little bit more sophisticated solar cells. But I will try to start with a small introduction, and then go to the topic of this morning. That is then for this multi-junction polymer solar cells. I tried to explain what they are, why they are, and how you can make them, and what is the advantage of that. So if you go to organic solar cells, it's next to OLEDs and transistors, the third main topic that people have been working on in organic electronics. And organic solar cells are from their device structure very similar to an OLED, but the operation is completely opposite. Instead of getting light out, you want to put light in and get electricity out. There's also another important difference, is that most, if not all, good working organic solar cells consist of two semiconductors that are mixed, usually in a, now maybe not really 1-to-1 ratio, but in a ratio that both have a appreciable concentration. And the reason for that is that in a single organic semiconductor, it's very difficult to make charges. So if you excite a single organic semiconductor, you get what is called an exciton. It's a neutral quasi-particle that is not able to generate free charges. And to generate these free charges, people have been using donor and acceptors that are two semiconductors with HOMO and LUMO levels that are offset, such that if you excite either of the two, you can make a charge-separated state in which the electron goes, for example, if you excite the donor, goes up, goes over to the acceptor because this level is empty, and you get a state in which the acceptor is negatively charged and the donor is positively charged. This scheme is very similar to what happens in natural photosynthesis. There you also have two molecules, a donor and an acceptor, chlorophyll and a quinone molecule, and between chlorophyll and the quinone molecule electron transfer happens. So it looks much like photosynthesis. The device is completely different, of course, because it's just a solar cell. And one crucial thing of such a solar cell is this bulk heterojunction. That is where you put the two materials together in one layer, and you have to make sure there's a lot of interface. The interface is really required to make sure that every photon that is absorbed close to the interface. If it's further away from the interface, the exciton that is formed in the pure material has to diffuse first to that interface to generate the charges. And excitons diffuse very little, maybe 5-10 nanometers, maybe 50 nanometers, but then they decay via intrinsic decay processes as going to a triplet state or photoluminescence or non-radiative recombination. But if such an exciton reaches the interface or is formed at the interface, it can form these charges, and then you need to transport these charges to the electrodes, and that's why this morphology is also important, because you need to have some kind of percolation pathway such that the charge can travel easily to the electrode. Now, for these positive and negative charges here that seems feasible, but if you have a positive charge that will be generated in this region, then there is no connection of that positive charge to this electrode, no direct connection. So that charge might recombine, might not be collected. So the morphology is very important in the end. Now if you do everything right, you can make a reasonable solar cell, and we'll see some examples later on. If you characterize a solar cell, it's typically done with the IV characteristics, so the current density versus voltage. And if you measure a solar cell, you usually measure it under light conditions, so you shine solar light, and we call that AM 1.5 if it has a certain spectrum. That is a spectrum that rarely happens, but it's a spectrum that scientists have agreed on, that this is the solar spectrum under a certain angle, an angle of about 48 degrees with the zenith. That gives a certain spectrum, and that spectrum at 1000 watts per square meter is a intensity that you would have on a very sunny day in summer, maybe here also in Poland, and then you get a certain light intensity. Now what you do in the lab is you try to make that light intensity as good as possible with the same spectrum. That is hardly feasible, but you can try it at least. And then you can measure a solar cell for its performance, and you measure the IV curve while you're shining light. And you get a curve like this red curve, which is characterized by a few important points. It's the short circuit current, the open circuit voltage. The short circuit current is simple. You short the device and you get a current, and that is the short circuit current. If you cut the wire between the two poles, then you get the open circuit voltage. There is no current running, you get the open circuit voltage. But as the power that you extract from a solar cell is the product of short circuit power is product of current density and voltage, both this point and this point give you zero power, because here the voltage is zero and here the current is zero, so the product would be zero. The only real part that is interesting is this, what people call the fourth quadrant. This is the part where the solar cell can operate without external source. So you can absorb, you can operate from here to here by putting a load in between. That could be a motor or a radio or whatever, your telephone in between, or a battery in between these two, and the load will push your IV curve to a certain point, and you try to make the solar cell work at its maximum power point. The maximum power point is this point. That is where the product of current density and voltage maximizes. Now, in general, people characterize a solar cell with three parameters. That is still this short circuit current, the open circuit voltage, and something that they call the fill factor. And the fill factor is actually the ratio of this pink area or purple area with the area that you have when you look at VOC, short circuit current density, and the 0 point here. So this rectangle is the product of VOC times short circuit current. This rectangle is Vmax, Jmax, this should be a X of course, and then the ratio of that is the fill factor. And then the efficiency of the solar cell is the extracted power, that is the maximum power that you can extract, that is Vmax times Jmax, or VOC times JAC times fill factor, divided by the in power. And if the in power is something like 1,000 watts per square centimeter, or that's equivalent to 100 milliwatts per square centimeter, then you can easily extract the efficiency. Now, just as an example, how does that look? This is a reasonably good kind of recent low band gap material. So you have a polymer, that is the donor, you have a fullerene acceptor, you mix the two in the right way. You have to do it absolutely in the right way, otherwise you get the wrong cell. And then you can measure the current density characteristics. You get this curve. This is the curve in the dark, so it's a nice diode. In light you get this curve, open circuit voltage, short circuit current, maximum power point somewhere here. And if you calculate of this curve the current density, fill factor, open circuit voltage, you get to an efficiency of something like 8.3. This is another important curve of a solar cell. This is what we call the external quantum efficiency. So the external quantum efficiency measures how many electrons you get for every photon at that wavelength. So example, at 600 nanometers we shine light. This laser is something like 630 nanometers, I guess. So if I would shine light from this laser on this cell, I would have, for every photon from the laser, I would have a little more than 50% of electrons, 0.5 electrons running. So it's not a very good solar cell in the sense that the quantum efficiency is not 100%, but it's also not so bad. It is 50%. The current could increase if we can absorb maybe more light, or if we can convert more charges. This doesn't really say where the losses is coming from. So we have here like between 50 and 60% quantum efficiency. Doesn't tell you where you lose it, but it tells you that you lose somehow some of the photons somewhere. It could be because they are not absorbed. It could be because they are absorbed by the wrong layer. It could be they are absorbed by the metal or by one of the contacts. It could also be that they do generate charges, but these charges just don't make it to the electrodes. Another thing that is quite general about solar cells in general, but not only about organic solar cells, is that you see that here you have a quite small band gap. If you calculate this in energy, the band gap is something like 1.35 electron volts. And you see that the open circuit voltage of the cell is lower. It's 0.6, 0.7 volts. So that means that you lose, even for the photons that are here, these photons have an energy of 1.3. If you measure what you get at voltage, you get 0.6, 0.7 volts. So you lose 0.6 volts also on that. It's even worse if you are here if you are at 400 nanometers, your photons have 3 eV energy, and you get only 0.6 volts back at open circuit in the maximum power point. It's even less, it's only 0.5 volts. So you put in a 3 eV photon and you get 0.5 volts back for it. That is not a good exchange. So what people try to do is make multi-junction solar cells to enhance their efficiency. And the idea of a multi-junction cell, I'll show on the next slide, just show that these single junctions, they have been increasing over the past few years quite steadily, and good efficiencies are still rising, and I'm pretty sure this will continue. We will talk about that later, how to do that, maybe tomorrow then. But if you look at a tandem cell, or what we call a multi-junction cell, is 2 junctions. So the idea of such a tandem cell is quite simple actually. You combine 2 cells on top of each other, one with a wide band gap and one with a small band gap. And so what is the advantage of that? Suppose you would only take the small band gap material, like in this cell. You would take this cell, it's a nice small band gap material, maybe. So you can absorb all the photons. You can absorb high energy photons, low energy photons. But as I said, if you absorb such a high energy photon in this material, you would lose quite a lot of energy to the band gap already, and then you still have to transform that energy into a charge, and you will lose more and more and more. So your energy loss for a high energy photon is quite appreciable. So it would be more advantageous to put such a high energy photon in a wide band gap cell, because a wide band gap cell can give you a higher voltage, so you lose less. Although if you just use a wide band gap cell, you cannot absorb the low energy photons. So the ideal combination is a tandem cell, or a better combination is a tandem cell in which you are able to absorb the high energy photons in a cell, in a wide band gap cell that gives you a high voltage, and the low energy photons in a small band gap cell that gives you a little less voltage, but still you can absorb these cells. So a tandem cell gives you per photon a higher voltage and gives you more photons to be absorbed compared to the single junction. So it's really an advantage. If you do look at the Shockley-Queisser limit, that is the limit for a solar cell performance, for a single junction it should be 33%, for a tandem cell it's already 42%. So it's really an increase of efficiency. And we'll show you also that that works also for organics. If you think that you can make an organic solar cell at 11% with these assumptions, you can calculate that quite easily. It should give you something like 11%. Then with the same assumptions, you can calculate a bit more difficult, but you can do it. You can calculate that the efficiency should go up to 15%. So that's a nice enhancement of efficiency. Now, one of the issues, of course, is if you make such a device, it's a little bit more difficult to make because you have more layers, and how to put all these layers on top of each other, especially because most organic solar cells and polymer solar cells are made via solution processing. So you try to solution process one layer on top of the next and try to see how that works. Now, that solution processing of layers on top of each other is not so easy as it looks like. You've all been to kindergarten and made drawings with paint, and then you figured out that if you paint over paint over paint, you end up with something brown, and it doesn't look very nice. So you have to be careful if you put all these layers on top of each other that you don't mess up the layers. And to do that, you have to carefully select not only the layer that you want to put there, but also the solvent or the conditions under which you want to put that, because every layer on top of another should leave the layer underneath, every layer underneath, intact. Now, that was a difficult nut to crack initially, so a PhD student already 10 years ago worked in our group on that, and he solved that problem for the first time. And basically we are still using his recipe, although we have kind of changed it a little bit over the time, of course. So what he said, I need to put these layers, and I put in between the two cells I need a recombination layer. A recombination layer is a layer where electrons from one cell recombine with the holes from the other cell to pass the current, basically, without a voltage loss. And that's kind of funny. So you need a layer that on this side for electrons has a low work function, and on this side for collecting the holes has a high work function. And so you need a layer that is on two sides, has a different work function. But there's no loss in between. So you can do this by taking conductive materials that have different work functions. And by the fact that they have a number of charge carriers in present, they align their Fermi levels. Without a barrier, you get some kind of tunneling junction in between that is very thin. And basically, you can align two metals in that way with different work functions. So he took for that, not really metals, but metal layers that at least have some kind of larger electron density, and one is p dot and the other is zinc oxide. So p dot for the top layer and zinc oxide for this layer. And zinc oxide, you can dissolve zinc oxide particles, something like 5 to 10 nanometer particles in acetone, and you can spin coat a layer on top of basically any organic layer. The difficulty of using solvents on top of your organic layer is that you have to be careful not to wash away your polymer or your fullerene. And acetone is one of the few solvents that you can use. Acetone, isopropanol, ethanol, methanol, water, and everything else doesn't work. So you have a very limited choice of solvents that you can put, but acetone is a quite good one. And if you have that zinc oxide layer, then you can put on p dot. The difficulty with p dot is that p dot is usually brought in a very acidic solution. It's a pH of 1.5, and the zinc oxide cannot withstand any acid. So you cannot put the normal p dot solution on top of a zinc oxide because you would just dissolve all the zinc oxide in the water. So what we did, we found a way to use pH neutral p dot and pH neutral. P dot is a special formulation that you have to make, because if you just neutralize p dot, you lose all the conductivity. But if you do it a bit carefully, you can do this. And that pH neutral you can put on top of your zinc oxide. So this shows an example. This is just a UV spectrum of zinc oxide particles on a glass substrate or a quartz substrate. If you put the normal p dot on top of that, you get a p dot absorption, but all the zinc oxide is gone. And if you do it with the pH neutral, you get both the zinc oxide absorption is still there and the p dot absorption is there. And then you can make such a recombination layer. And the first cells that we made, so this is 10 years ago, we took old-fashioned, at that time, still quite in use, PPV material and the polythiophene, and you could make two cells out of that, and if you combine it, you get something like an IV curve. And actually, we were very happy with this, because it was kind of a 2-year work to get to this, and it was a tandem cell at that time that had not a very high efficiency. The maximum power point is 1.8, so it has 2% efficiency, nothing really spectacular, not even at that time. But we were quite happy to make such a tandem cell. Of course, then you want to improve this, and so we set out to improve it. Maybe just one thing to mention is that in such a tandem cell, it's easy to always see that in a tandem cell, your open circuit voltage should be more or less the sum of the two subcells. So this is the purple subcell, this is the PPV subcell. They give efficiencies of 0.75 and 0.82. Open circuit voltage of 0.75, 0.82, and if you add that, you get close to this 1.5, of course. It's not exactly the sum, but it's fairly close. So you don't lose much voltage by this interconnection layer. That is an important thing. Of course, your short circuit current will always go down if you make a tandem cell, because you have to divide your photons over this layer or this layer. They can only be absorbed here or there, and the total current is measured as one current. So a tandem cell doubles the voltage, you could say, but halves the current. And because you have this trick of getting a little bit more voltage out of your wide bandgap material, you in the end get a little bit more voltage than you lose in current, basically. That is the idea of a tandem cell. So we tried with some, at that time, this is 7 years ago, a little bit more modern materials. At that time we had a wide bandgap material, this one, which gave us 4%. We had a low bandgap material, this one, which gave us 3.5% or 3.6%. And you can see that the low bandgap material gives a lower voltage, the wide bandgap material gives a higher voltage. These are the single junction IV curves of these cells, and they are, at that time, definitely pretty okay solar cells. So the idea was to see, can we combine this now in a tandem cell and increase the efficiency above what we have. We have 4.2, we have 3.6. If you combine them, the idea is this should work. Now, to make that work, you have to optimize it. So one of the issues with a tandem cell, go back to this scheme, is that you have to make sure that this layer and this layer generates the same amount of current, basically. It's a device like this, there's two batteries in here, and if they are both working, the device works nicely. If one battery is bad, the total device doesn't work at all, because one battery can make a voltage between the two, the other cannot sustain a new voltage at the same current. So you have to make sure that if you pass current, that this cell is generating the equal amount of current as this one. You can compare it a little bit with such an old-fashioned line of trying to extinguish a fire with people passing buckets. And if there's one person that cannot pass the bucket because he is a bit of slow, yeah, there's a big pile-up of buckets at his feet, and the fire doesn't get extinguished. So you have to make sure that all the people in the row have the same ability in passing buckets. And there's the same for such a solar cell. You have to be able to pass the current, so they have to be almost equally good. And to do that, to make sure that you do that, you can play around with the layer thickness, because if you make a layer thicker, it can absorb more light, it can make more current. If you make it thinner, it can generate less. So by changing the thickness, you can balance these cells. And how to optimize it is, in the end, quite a trick that you can do in your computer almost, if you have the right data. So what we do is we measure the optical constants, so the refractive index and extinction coefficients of all the layers. We know what the solar spectrum is, and by optical modeling with a transfer matrix formalism, you can calculate then how much photons you would be able to absorb. That would be the maximum current that you get. If you get for every photon an electron, you get the maximum current. Then we also measure the short circuit current density for all these thicknesses, for our number of thicknesses, let's say 5 or 10. And from this maximum and the measured one, we get what we call the internal quantum efficiency. The internal quantum efficiency, it says how many electrons do I get for photons that are absorbed in my active layer. And I get then the internal quantum efficiency. And I also measured these IV curves at different density, and we normalize them. So we set the voltage to 1, and we set the current to 1, and we normalize them. It's kind of a funny way of treating your data, but the current is set to 1, and the voltage is set to 1. Then you have basically gathered all the data, so optical constants, internal quantum efficiency, and normalized IV curve, and then you can do a kind of calculation. So you just build your stack in your computer, and you put in the optical constants, solar spectrum, you get the maximum current density that you have for the two layers, thickness 1 and thickness 2. You put in the internal quantum efficiencies at these thicknesses, and you can calculate how much current you would generate in one layer, how much current you would generate in the other layer. Then you put that into the normalized IV curves. You get the IV curves of the subcells, and when you know the IV curves of the subcells, you can add them to really make an IV curve of the tandem cell, and from the IV curve of the tandem cell you can calculate the open circuit voltage fill factor and efficiency as function of the two thicknesses. And basically you do that for all the thicknesses that are relevant, and you get a picture like this. So this is the back cell thickness and the front cell thickness, going between 60 and 150, and this something like 70 to 250. And you can calculate for that thickness the current, the voltage, the fill factor, and in the end the efficiency. And you see that the maximum efficiency here is found at this point, more or less, and that is the point where the cell would operate, the two cells would operate the best together. So you need to balance the cells. It's not the point that this red curve that I show here is a curve that is just the curve for current matching. People always say you have to make current matching. That's also what I said a little bit in the beginning. You have to make sure that they both pass the same amount of buckets. But it's not entirely true. You have to do a bit more than that, because also the voltage and the fill factor play a role. And so you see that the maximum, or the current matching doesn't bring you always to the right point only. So you need to do this whole optimization. You get this point, and then you make such a cell with these active layers, and you said, well, we expect then an efficiency close to 5%. That's actually what we found at that time. So you put in, this was the calculated performance and this is what we measured in the end, and you see that the correspondence is very nice. It's close to 5% tandem cell. This is the quantum efficiency. You really see that both cells contribute to this. The wide bandgap cell mainly absorbs the blue and red photons, the visible photons, I would say, and the other cell, the low bandgap cell, takes the near-infrared photons. And also this efficiency was slightly larger than the best efficiency that we could get with the single junctions, so that's a good thing. Of course, then time passes by and you try to make better layers and try to optimize this. Before I show that, it's good to show such a cross-section of such a tandem solar cell. This is a TM cross-section, so you glass substrate, ITO, p-dot layer, first active layer, zinc oxide. Difficult to see here, but there's a p-dot layer. Then there is the second active layer, aluminum back contact. And here, if you zoom into this recombination layer, you can think that you can actually see kind of nanoparticles sitting there. And you see some kind of very thin layers, but they're all there. And actually we processed the initial part, we can process several cells on top of each other. It's not restricted to 2 cells. I'll show you that also a bit later. So then we're now here, I think 2013. Materials get better and better. So we have now 2 materials that are giving you close to 6%. This is a wide band gap, 1.9. This is a small band gap, close to 1.3. The idea of the cell is still the same. P dot as bottom contact, first active layer, zinc oxide, pH neutral, second active layer, back contact, and you make a solar cell. So again, we do this optimization of the thicknesses. We find now that we should be able to achieve powers close to 9%, and that's also what we found. I think this goes up to, it says 8.6, but here you can see the value that we got is 8.9%, and this was the solid blue line is the one that we measured, and the dashed blue line is the one that we predicted, and so that fits nicely. And again, you can see that the 2 parts equally contribute. And the difference compared to the previous one is that we have been able to get the quantum efficiency up here to 60%. And if you compare this to the previous one, the quantum efficiencies here were 40%. So that really increases the current. Maybe a few other things also improved. Materials were better, and you can make a better solar cell. So then we also, this is more recent, we tried another wide bandgap material, and we had the hope that we could make a 10% solar cell here. This efficiency optimized here would be 10% with this small bandgap material, this wide bandgap material. But somehow we never got there. We got close again to 8.9. This should have been, so the predicted line is here, the dashed line. The solid line is the measured one. We lose a bit of current, we lose a bit of voltage, and we lose a bit of fill factor. And yeah, where that exactly comes from, we never really figured out. But the total efficiency was somewhat less than we expected. Sometimes these calculations, do not really work out as good as we hope that they would do. But in general, they give a good ballpark figure of where to go. So this was another material combination that also gave a 9% cell. And these tandem cells, this is the single junction cells, the green one. The tandem cells have been lining up now pretty nicely. I think there's maybe already a new dot of 12% of a tandem cell now that I didn't put in the figure yet, but should put it in 2016. So these are increasing, and I think with more materials being developed, tandem cells will surpass the single junction line at some point. Now one thing that we have been doing this for is this following question, a bit a detour out of solar energy maybe, but or not a detour, but detour out of solar cells, is that this is a kind of nice graph. If you look at this, this is where in the world the sun shines. As you can see, neither Holland or Poland receives any sunlight. Appreciable, really, if you want to have real sunlight, you have to go to Australia or to the Sahara or Argentina or Texas or something like that. And this is the places on our planet where light is, or where electricity is used. This is the light emission as indicator for electricity demand, and you can see it's completely the opposite. So It's also time-wise it's the opposite, maybe for some, if you look at lighting at least. So solar energy is there where we don't need it, at times that we don't need it. So you have to kind of solve this problem a little bit in terms of storing it. So storage is part of this challenge. That's where we came in to look at artificial leaves. So artificial leaf is something that would generate a chemical from solar energy. And you can try to do a photochemical reaction, but you can also try to use solar energy to do an electrochemical reaction. So then you need a catalyst to convert water into hydrogen or carbon dioxide into methanol or something like that. And if you have such a tandem cell, you can think of a tandem cell works a bit like this. You have two photons, they give both an electron hole pair. The electron hole pairs in the middle recombine without losing too much energy, and you end up with an electron in a hole that should be enough energy. If it's more than 1.3 volts, 1.23 volts, it should be able to split water, to generate. So if you throw such a tandem cell into water, you should be able to get hydrogen and oxygen. And that's a way of storing energy, solar energy and chemicals. The real life is a bit more difficult, of course, because water splitting comes with overpotentials. Overpotentials are additional potentials that you need to get a certain current density at an electrode. And it depends on the type of electrode materials that you choose, whether these are higher or lower. If you take a very good catalyst, and that is platinum for hydrogen and ruthenium oxide for oxygen, then you can have a pretty low overpotentials. I should say that the overpotential also depends on the current density, so you have to take these numbers a bit with, okay, I need to know the current density at that point, otherwise the number doesn't say too much. There's also other materials, these are typically very expensive materials. There's also more cheap, earth-abundant materials, nickel, molybdenum, zinc, and cobalt oxide you can use, and then the overpotentials are somewhat larger, but you can still split water. So if you take our tandem cell at 8.9, we had this curve, and then you ask a question, well, if we have a tandem cell, we have 1.5 volts at open circuit voltage, but not at the maximum power point. At the maximum power point, we are below the 1.23 volts, and definitely below the ones that if you add the overpotential. So with such a tandem cell, you cannot yet split water. And so then we said, okay, then we need an extra junction to get extra voltage, so you need 3 cells. So the first try that we did was this one, was a triple junction, we call it the first attempt, was this somewhat older material and this somewhat newer material that we used. And then you can make a triple junction solar cell with 3 layers. And to show you how that works, these are the single junction. This is the wide band gap, the small band gap and the wide band gap material. The wide band gap material was not the most perfect one maybe, but at least it worked for this cell. So we had a small band gap giving 4.5. We have a wide band giving 3.6, and if you make a tandem, well, you don't actually gain much compared to the small band gap in efficiency, but at least you get a higher voltage. If you now add, this is 6 solution process layers, we had to put in an additional layer on top of this neutral p dot naphion, because the neutral p dot has a work function that did not match with this material, so we were losing voltage there. The work function of the neutral p dot is too low, and to increase it you can put a very thin layer of naphion on top of it. It works, it helps you 100 millivolts, but that's just enough to get the cell to work better, and then you get this 4.6%. And if you put up an extra junction, so you put now additional layers, you need 10 solution process layers on top of each other, then you get to an efficiency of 5.3%. It's not very high in terms of efficiency, but it's nice because the voltage is now good enough. If you now look at this IV curve, the open circuit voltage is 2.3, and at the maximum power point we have 1.7 volts. That is enough to split water. And so that's what we did with the cell. It's kind of a very simple experiment. You just take 2 platinum electrodes, you hook it up to the solar cell, and you can split water. You can see these are, and you can actually measure, if you take these 2 electrodes, you pull them out of the water, you get the open circuit voltage, and then you put them in and slightly lower them, and you just track the IV curve basically, or part of the IV curve, until to this point. You cannot, if you go them, put them deeper, doesn't help, because here you're at the potential at which with 2 platinum electrodes you can split water more or less, in a very simple experiment. Okay, that needed to be improved, of course, and so we set out to try and make better triple junction solar cells, and the first one was with these materials that we already used for a tandem cell, and tried to make improved triples. So what you do then is you add this extra layer and see how that works for your efficiency. And then you have to do, if you do it in the correct way, you have to do this calculation that I explained a little bit. For 2 layers, you have to do for 3 layers. So you have to do for every layer that you put in your device, you have to gather all the data, and all the data are put into a computer program basically that calculates, depending on the thickness of the front cell, the back cell, and the middle cell, where you have to be. Now, this is a kind of difficult graph to understand, but you can see that while you go to this red spot here, you get to higher efficiencies of close to 9% when you have front cell, middle cell, and back cell of these thicknesses. Now, if you make that, then you can make we call it again a 1+2 triple, because the 2 small band gap materials are the same. That also explains that the first one has to be thin and the second one has to be thick. The first one has to take part of the spectrum, and the second one has to take an equal part, but since already quite of the photons are taken out, this layer has to be thicker. So you see that the middle cell is quite thin, but the back cell is quite thick. And if you make that cell, you predict efficiency close to 9%, and that's also what we get. So we get a 9% triple junction solar cell with a number of solution process layers only. So that works. And then you can use that cell to split water. So this is maybe a difficult graph for those that haven't seen this, but the one that I know about electrochemistry should recognize this is a tafel plot. So the tafel plot plots the overpotential that you have for the reaction as function of the logarithm of the current density. And this is then, for example, the line for ruthenium oxide for waters, for hydrogen production, so the hydrogen evolution reaction. This is ruthenium oxide for the oxygen evolution reaction. So, and these are different current densities or different areas of the cell at which we get a certain current density with a certain area of the electrode. So, and for small scale cells, we expect a rather small overpotential and a little higher overpotential if we use these cobalt oxide and nickel, molybdenum, zinc. These are kind of earth abundant catalysts, and the blue lines are higher than the red lines, which are the more optimized materials. So if you then take such a tandem cell and you basically throw it into water, or you connect the ruthenium oxide electrodes, the cell moves by itself. So you put it in water, you shine light, it moves, so the red line here is the IV curve, and it moves over the IV curve to the maximum power point. There it stops. It's designed to go there, and it exactly does what we wanted to do. So the operating point of this, with these catalysts, you get to an operating voltage of 1.49 volts. You get, this is the current more or less, and you get then solar to hydrogen conversion efficiency. That is basically the current density. I'm not sure why this is now 4.09 times 1.23. I have to check what is the 4.4. Maybe it's just a typo. This is the short circuit current density. If you look at the maximum power point, so this cell, by the virtue of its catalysts, works in this point, and this point is very close to the maximum power point of the solar cell. So 1.49 and 1.43 is a very small difference in voltage. The maximum power point current density was 4.6, and here's 4.4. So we designed it quite nicely to end up in the maximum power point. This is the curvature versus time. So the cell needs a little bit to set up the electrochemistry layers, and to it needs a bit of time, but then it stabilizes fairly nicely for the rest of the time. and you can get an efficiency of something like 5% to convert solar light directly into hydrogen. You can also do it with earth-abundant catalysts. Efficiency goes down a little bit because here you have an operation point that is a little further away from the maximum power point. It's now 1.56 volts, so you lose a bit of voltage. That makes also that you move up the curve and you lose current, and that also makes that the efficiency goes down, but it also works. And in practice it looks like this. So we have a triple junction that is directly connected to catalysts. We can put it on a platinum or a titanium substrate, but you can also put it on direct on ITO, and basically you throw the cell in water and it starts to bubble hydrogen and oxygen. We do it with a lead to make sure that we can extract information from it. If you don't measure the current or the voltage, you cannot measure anything. You just throw in water, you see the bubbles, and that's it. Or you have there's ways to do it, but it's easier when you can collect the current somewhere in between. But if you don't, you can also make this kind of fully integrated device where you see here this green part is the triple junction solar cell. This is the back electrode. It's a fairly 3 by 3 centimeter device. These are ITO contacts that are in direct connection with the solar cell, the top layer and the bottom layer, and you see hydrogen and oxygen being produced at these electrodes when you shine light. So that works. And then the next part of the story was to see if we could make real triple junction solar cells with real 3 different layers. So far we did 1 plus 2. It's kind of a trick if you don't have the right material, but we set out to try and make with 3 different absorber layers triple junctions. We have some materials that do pretty well in the really almost near infrared, so you go beyond 1000 nanometers. The absorption here is fairly similar to that of silicon for this material, but the efficiency is pretty low because the voltage of such a cell is quite low. But still in a tandem cell you can, or a triple junction cell, you can try to make it. And now that worked pretty nice. Here is an example of the structure that we made. At least it works in the sense that we can predict a certain efficiency of 8% for this cell. Again, with optimizing the different layers, we were expecting to get 8%. And also here we failed to really get that number. We got something appreciably less, and make a very difficult device end up with 6% by this time. This was done in 2015. We knew how to make already 7 and 8 and 9% cells from single junction. So then if you make a very difficult stack and you end up only with 6%, it's a bit of disappointment. But at least you can make it. We can measure these quantum efficiencies very nicely. You can see all the cells contribute. There are some contributions that you would not like. There's all kind of small and bigger problems with this cell. But at least it's a triple junction cell. It's a triple junction cell with efficiency that goes all the way, or with a response that goes beyond 1000 nanometers and still has an appreciable efficiency. Of course, we weren't trying to change this, and one of the problems that we have, I'll show you this piece of cake later, but one of the problems that we have is this pH neutral layer. This pH neutral P dot, so we have 1, 2, 3 P dot layers, and P dot starts to absorb in the near infrared. So we wanted to get rid of the P dot in some way, or at least have less P dot. And that was kind of a way that I'll show in a minute. So this Alice Fern, she was Italian. She was also very good in cooking, and she made a triple junction birthday cake. So here you can see it's kind of nice. It's a real cake. I ate it, so it was not only looking nice, but I really ate it. So it has 3 different band gap layers, bulk heterojunctions, as you can see, between blue and some whitish. And then there's a nice recombination layer here of whitish and other materials. So it has all the characteristics that are there, except that it does not convert, let's say, sunlight into electricity, but it gives a good taste and gives you at least some energy, such a cake, to eat it. It was also not so easy to make it, I heard how to, but I wouldn't be able to do it at all, of course. So in the meantime, also other people have been working on this, and this is a nice paper from Yang's group in California, where they also made a triple junction solar cell. They get to 11.6 for a triple junction. with 3 different materials, and they use here a different layout. So they use a layout where the zinc oxide layer is at the bottom and the aluminum layer is at the top, and that makes that the polarity of the device is different. So you have now the electrons at the bottom, the holes at the top, and you need to process all the layers differently. They show a very nice nice solar cell. So also based on this idea, and we had the idea already, we made some tandem cells in what we call an inverted configuration earlier. We set out to make a better triple junction solar cell. So this is one where we now are with wide band gap, middle band gap, and small band gap materials. This was calculated to be a 10% solar cell, again with this optimization of the layer thicknesses. You can calculate that you should at 10%, this is the predicted line, and the measured line is slightly different in VOC and short circuit current, but in the maximum power point it levels out the differences and you get to the efficiency that you predicted. And actually kind of nice to see this graph. This graph looks okay. It's another graph, but it took it's quite some effort to do this. And this is a measurement of the external quantum efficiency. The red, green, and purple dots that you see are the measurements, and the dashed line that you see in between is the one that we predicted. And so it was made before. So you do all the subcells and you put everything together in a computer program, and you say this should come out. And everything works pretty nicely except for the green one where you see a bit of offset, so we get somewhat lower response there, but the shape is actually okay. And I should say these things look like maybe this up and down looks like noise. It's not noise. It's really, if you change one layer by 10 nanometers, this pattern looks different there because of optical interference. So it really shows that we master almost all the things except that we lose a bit of current somewhere. I was kind of very pleased to see this. So this was last result of last year of December. Okay, and he could also make these triple junctions. So Dario could also make these triple junctions into kind of module. So here you interconnect all the cells and you get a 4 times triple junction cell with a voltage of 8 volts and a power conversion efficiency of 10%. That gives a nice IV curve. Last few minutes, if I'm allowed. 2 more minutes, 3 more minutes. I go very.
Even more. You have 7 minutes.
7 minutes, okay. Then I'll go a bit on what we have done with colleagues from Delft University in hybrid solar cells. So our colleagues in Delft are very good in making amorphous silicon. They have a long history of amorphous silicon solar cells. And amorphous silicon solar cells are actually quite nice wide band gap solar cells. They give you efficiencies of close to 10% with good voltages, good fill factors, and here's 3 examples of 3 slightly different amorphous silicon layers that have different absorption coefficients. So we said that we have these nice small band gap materials, you have these nice wide band gap amorphous silicon, so why don't we try and make a tandem cell? So that's what we did. So we combined the amorphous silicon with the small band gap material, and we made together a tandem cell. So this is glass and ITO, then and the zinc oxide. So it's an inverted cell. So the negative contact is at the bottom. Do I say this right? No, sorry. The positive contact is at the bottom. I say this wrong. This is a zinc oxide, aluminum doped zinc oxide. Then there's a amorphous silicon solar cell. Then on top of that there's another layer of aluminum doped zinc oxide. Then we come with a very thin layer. This entire thick or darker layer is this combination of a very thin layer of silver. It's 1 nanometer of silvers to enhance a bit the contact between the zinc oxide and the molybdenum oxide that we put on top. On top of the molybdenum oxide we then put our photoactive layer, and then we put aluminum and silver as the back contact, and we get a tandem cell, and that tandem cell actually gives nice efficiency. So these again the single junction IV curves, the tandem IV curve, and the 2 external quantum efficiencies of together 11%. And again all these undulations that you see here are really due to optical interference. So you have to do a pretty accurate calculation to balance the 2 cells. If you change the thickness a little bit, this really can drop to half, and so you really have to balance it carefully to get to high efficiency. You can also make this into a triple junction, so this is even more difficult then. So what we did is, or what they did, I should say, they made first a amorphous silicon tandem cell. So and then the difficulty is that you have two layers of amorphous silicon that have more or less the same absorption. So you have to be really careful to absorb a lot of light. So what is done, we textured the zinc oxide to have a bit of light scattering and make sure that and diffraction, make sure that the first layer of zinc oxide, of amorphous silicon absorbs a lot of light. And then we take a second one, which is really thick. So the first one is something like 100 nanometers, the second one is 1000 nanometers. It's difficult, or it's impossible, I should say, to see where the front and middle cell go over in each other, because this is the cross section, it's just one gray area. This lower part is the zinc oxide. Here are two cells, and on top of that cell we put again, on the amorphous silicon solar cells, we put again this recombination layer of aluminum doped zinc oxide, silver and molybdenum oxide, that is this dark part. And then you see that you have to make, that's why we made it mildly textured. If you make it strongly textured, you can absorb more light, but you end up with very high surface corrugation here, and so it's difficult to make a polymer layer that has no protrusions. And so we had to take mildly textured zinc oxide, where you can at least make a closed layer of your polymer solar cell, and then connect it with a back contact, and then you can get to 13% tandem triple cell. It's kind of a complex cell, of course, but it just shows that if you try to push the limits in terms of efficiency, in terms of materials choice, you can really get to interesting materials. And there's, of course, to me it's a bit like an example. If we are able at some point to make organic materials that have these characteristics, and we are not that far from there, then we can really push the efficiencies of these tandem and triple cells to efficiencies, I think, close to 15% in the, for sure, and beyond that, I first want to see to make predictions after that. So organic and hybrid triple gel cells have now reached 13.2. There's also a report from Heliatech company that they have a 13.2 fully organic triple junction solar cell. So that is actually this point on the curve. And so there's quite some improvement there, and yeah, this also has the tendency to still increase. So difficult to say how far and how long it will increase, but we'll see. So conclusions for the multi-junction. So this looks like a multi-junction cake. It looks how difficult you can make these things. You really have to pay attention to all the layers and to the interlayers and to the top and bottom contacts. So triple junction polymer cells, Yang showed a material close to 12%. Triple junction with amorphous silicon, you get a little higher at this point. They both can go to 15% for sure. Best materials for triple junction are approaching the relative criteria, the relevant criteria to get to this 15%. This is something that I'll talk about when I talk about the photophysics, because we still lose in organic solar cells too much voltage in my view, and that we have to correct, and we need to further increase or decrease absorption losses and losses in the contacts to make all these cells work still a little bit better. If you are very critical and you look carefully, you see some losses everywhere, and no, you can try to get rid of these at some point. Okay, I'd like to thank, there's a lot of people that contribute, but I think I put the most important people here in this list. Jan Gillot was the PhD student who made the first tandem cell in our lab, and Dario Di Carlo is the last one who's doing this so far, and all the people in between made very important contributions to that. With that, I'd like to thank them and you for your kind attention.
Very impressive. Indeed, God made the sun, and then Janssen made the solar cell.
I don't know.
We have got eminent electrochemists here in the audience, so I expect discussion on this electrochemical part of this your presentation. So, which electrochemist will ask the first question?
I'm definitely not an electrochemist. I apologize.
Okay.
You say you throw your devices into water.
Yeah.
I surely kill devices.
Yeah, yeah.
What kind of encapsulation do you use?
Okay, Of course, you need they need to be encapsulated. That is for sure. That you cannot just throw the. So this is actually quite simple. We just use a UV curable resin at the back. We put it on top of all the cell. We put a glass slide on top of that. We cure it, and then it stays okay for a long time. Actually, it's a quite simple procedure. It stays okay. Well, half a year you can store them in without. A solar cell is not that sensitive. The back contact depends also a bit what you put on back contact. We usually use aluminum, but if you put a somewhat thicker layer of silver on top of that, it also protects the aluminum. The aluminum is the most vulnerable to water and oxygen. It's the funny thing about organic solar cells. If you look why they degrade, it's usually the inorganic materials that performs the worst, and that's first is the aluminum that the contact that goes bad, and there's some kind of interface, and then of course at some point also the organics give in. That's for sure. But it's usually the contacts that go bad first, or it's the morphology of the active layer. If you just heat the cell becomes warm, then morphology can change also. The stability is an issue. Of course, I'm not saying that this is like stable indefinitely. That is not true, but it works pretty well.
Professor, I have a question. I'm not convinced that your catalysts are optimum for water splitting.
No, that might be.
You lose a lot on hydrogen, I think. This is a nice catalyst, non-platinum, for the hydrogen evolution, but I think you have pretty high overpotential. I'm not even sure if it's stable in long range. Oh,
this could be. Yeah. So ruthenium oxide, we haven't looked into the stability. If you just look at, we did also, of course, with the catalysts themselves, we do experiment. We just apply potential, and so you see that the catalyst is.
Cobalt. You're using cobalt and nickel.
Yeah. So that is the second. So this is the second one. That's a bit more difficult.
Is that an alkaline medium or?
This is alkaline medium. Yeah.
But I just wonder, because basically speaking, you have some kind of a polymer cell tandem or
triple.
triple. Let's say if one of the connections would be a true photoelectrochemical cell with a semiconducting material, stable enough, even if there are some, the efficiency is pretty low because you have electrolytic cell separately, integrated with a very nice solar system. I just wonder if to integrate
that's a very good question.
System, or we can offer that photoelectrochemical part.
So I know there's quite a few people that work on photoanode, photocathode. So where the semiconductor is both the light absorber and also the material that is in contact with the water or with the electrolyte at least.
Because you truly need at least a tandem cell.
Yeah, you need a tandem cell. Yeah, so that's. No, that's true. You need a tandem cell also. So, but our reasoning was a little bit that if you look into the literature of these photoelectrodes, photoanode, photocathode, you often see that people use a semiconductor and put on top of that still a catalyst to get the electrochemistry going better. And the only thing that we do say is, okay, let's put one other layer in between, and that is basically the electrode. So there is not, conceptually, there is not a big difference between a photoanode, in my view, that you decorate with catalyst particles to get the reactions going better, because most of the photoanode materials also have overpotentials that you want to deal with. And basically what we say is, okay, if you just put one other layer in between, it could be a silver layer, and why not a silver wire or something. So it's so the other question that I often get here is, why don't you just make solar cells on one place and make electrochemistry on the other place? And I think the difficulty is, also there I don't have a good answer, so this is just trying to see what we can do. But what surprised me actually was that to get to low overpotentials, you really need large areas of electrodes. So your electrode area, in these examples, the electrode area is much larger than the solar cell area. It's like a factor of 10 different at least. And if you make the solar cell area equally large, or you make the catalyst area smaller, your current density through the catalyst goes up, and that translates into these tafel plots. So if you have this is for ruthenium oxide. So if you go, let's say, 1 order of magnitude in area smaller, you lose close to 200 millivolts in overpotential that you have put into additionally, and that is quite a loss in energy in the end. So the balancing of such a photovoltaic water splitting system, whether it be solar cell and electrochemistry or photoanode or something in between, I think the balancing of that in terms of dimensions for larger application is not really clear to me yet. What is the optimal there?
I have a feeling that from the water splitting point of view, it's a kind of a deadlock, because from one side, if you use an electrolytic cell, even if you use iridium oxide or some kind of alloys, which are supposed to be the most active, they are still corroding.
Yeah.
Because you really have to apply large overpotential, I mean large potential difference. If you go to photoelectrochemical cells, some semiconductors are stable, but then you deal with either the problem of what light you should use, or it's a question of efficiency. So it's a kind of a difficult situation, but maybe combination with your polymer system may
it could be
make it system not expensive enough in the longer run, possibly.
Now that's one of the ideas, of course, that we have, is try to see if you can there's also the reason why we use these earth abundant materials, to see if with cheaper catalysts you could think of making something that would be cheap in the end. But I'm also not really sure that this is the right way to go. I see all the problems that are there, and
but you have 12% efficiency in solar parts.
That's
we are running out of time because the discussion is over 10 minutes. You have one short